So I recently went down to my electronics recycle center and made actually 3 trips to recycle a bunch of stuff, electronic stuff, and just kind of went and looked at what they had on the floor, and I came across these 2 RAMCHECK devices. And you know, this one was kind of cute. It'll test 256K and 64K, but honestly I can test those in my retro chip tester. So this alone didn't have a whole lot of value for me, but this was sitting next to it, and it says access time times 10 nanoseconds. And there's a switch here that'll go from 150, it's 0. So 150 nanosecond, 140, 130, all the way down to 10 nanoseconds. And then it'll change VCC, 5 volts, 4.55 and 5.5 volts. So you can change VCC. Why you'd want to go to non-regulated, I don't know. I think that's what that stands for. Anyhow, I spent a bunch of time looking at these. Decided to buy them because I was intrigued by the, quote, the VCC margins ability here and the speed ability here, and started looking for manuals for them, and still haven't found manuals. Cannot find manuals. Lots of confusion. This guy seemed to work. I could put a part and it would identify it as 256K or 64K. It would test it as good or bad. It seemed to work just fine. This one I'd put a part in, it didn't do anything. It's got a single red LED and nothing made any sense, and I couldn't figure out how to use it. Both unit has its own power brick, so they both have a hard attached power brick. That was part of what also caught my attention, is the power bricks are hard wired in, so I know I've got the right power bricks. So lots of confusion was actually resolved by looking on eBay, and there was a new old stock one of these with a 1 megabyte, I think, add-on module, and the 1 megabyte add-on module had this same cable, and in the picture it was shown connected like so. And I went, oh, maybe that's how this hooks to this. I've tested that. This is correct. This is how these two get hooked up in the end. Your part to be tested goes in here. Of course, the test switch is the test switch, and you can set the speed and the voltage you want to test it at. So I thought that's pretty cool. So we'll demo this in a second and talk about why speed matters. So I've got to head and back the screws out of both of these just so you can get a look inside. This has got an 8085, I believe, processor in it. Or no, it's an 8088 processor. There's an EEPROM here, 1989. There's a 8228, I believe, here. 82, why can't I read it? 8284. I believe that's a 2-phase clock generator to power to clock the 8080, if I remember right. There's, of course, a crystal oscillator. There's some TTL logic. There's some little add-on board here that's connected over the top of what looks to be maybe a DIP IC, or maybe it's in the DIP socket. It's hard to say. Maybe it's a double-sided load board. Don't know what the board is. I'm sure it's some kind of patch. There's a bit of wrap wire here. So there's definitely some kind of kludge kind of thing there. And, of course, the power cable straight out the back. And just a couple of normal switches down here. There's a larger cap here. Test switches over here that I don't really know what the switch does. Maybe it's filtering for, since the power comes in over here. I just don't know. It's hard to say, but let's go ahead and put it back together. It's got these 4 longer screws. I'm going to drop them into place. I've got a nice WIA, W-I-H-A, German-made screwdriver. I've had these for probably 15 years. They are a great set. So always with these tapping into plastic, turn it backwards till you feel it drop into the original cut threads, and then gently tighten it up. I'll turn it backwards here, and perhaps you can hear the pop. That little click was it dropping down into the original threads. I was turning it backwards with putting slight pressure onto it. We'll do one here again. Okay, that one was much more subtle, but I felt it drop and I heard it. We'll go around again. Again, it's subtle, but I feel the little click. And this way, I'm hopefully turning the screw back into the original threads that were cut when the screws were originally driven in. And that way I'm not destroying, wearing the plastic out. This one, what's inside of it? There's, of course, the rotary switch here that selects the position 0 to 15. These are typically binary output. This one must be a binary output. There's a ground and 4 pins here, or 4 wires. It's got to be a binary output. There's the rotary switch that selects various voltages. There's no the power switch is built into the rotary switch here. Handful of TTL logic. There's a voltage regulator. Say a handful of TTL logic. I believe that's probably a PAL there, some kind of programmable logic device, most likely. I think you'd almost need that to get the accuracy for the speeds, perhaps. Perhaps you wouldn't. Again, I don't know what the schematic looks like for it, but let's go ahead and put it together here. There's no reason not to. Though I guess for the demo I didn't need the screws in. And the same thing backwards until I hear the click. And just snug. Yeah, the click on these is much more obvious. Okay, that one doesn't want to click. We'll come back to it. I can tell by the height of this one, I don't think it's dropped down into the... I don't think it dropped down into the hole that originally was threaded out of, just based on the height of it. There it dropped. And there was the click. That one just had a hard time getting centered up. So let me go ahead and plug these in. So there's 2 wall wart adapters for them. They're both off. We will jumper them together. Bring up the power. I don't know if there's an order or not to it. I'll set this to 150. So it's set for the slowest speed. We'll go to 5 volts, which is very typical. We'll drop in a 256K DRAM here. And we'll test it. And you need to watch the displays down here. So 256, so it tells me 256. If I hit test, you see that center or that top segment come on, 256. That looks to be what happens when it's a good device. So that's very repeatable. And I'll show you why I believe that here in a second. Also, if there's no device, it goes straight to E, which I assume is for error. Let me locate a 64K. I know I had... Well, I got a bunch of them in here. It's just a matter of spotting one. Need some magnification. I forgot to. Yeah, it's an Oki M3764. It's a 64K DRAM. And it'll identify it as such. Test. 64K. And notice this one that it's the lower LED, or the lower segment that lights. I think that's when it's testing, and then it tells me, 64 for 64K. So I believe, those are 2 good parts. So you may be asking, why does speed matter? And why does the VCC voltage matter? And let's talk a little bit about that. So if you go to like a Commodore 64 with a 6502 processor, I believe it's clocked around a megahertz. Any speed of DRAM, probably at 400 nanoseconds or faster, is going to work in that. So just having random 64K, DRAMs and replacing one, it's probably going to work if it's a good DRAM. Speed is probably not going to be an issue. And on machines with slower clock speeds, that's generally going to be true. But as the technology moved forward and we begin to clock CPUs faster and faster, we got to 4 megahertz Z80s. And speed starts to become important because the faster the CPU clocks, the faster it expects the data to be returned from the memory. And the memory has an access time. It takes some amount of time for the data to be found in the correct storage area inside of the RAM and delivered out of the pins onto the bus accurately. And if you look at a data sheet for any kind of memory, SRAM or DRAM, you will see a bunch of waveform diagrams in the back, and there'll be things like TACC and TCE and TOE perhaps, and TACC is time access for TCC is address change. So when an address changes and the part's enabled, how long does it take to get stable data out? Or TCE, or there'll be something like that, is after chip enable comes down and the address bus is stable, how long does it take to actually get valid data out? And it takes time. Nothing is infinitely fast. So looking at this OKI data part, I wish I could show you this. It probably won't show up. It is an M3764-15R8. And you probably won't be able to see that. But the big tell here is the -15R8 after the 64K. That, to me, that -15 says it's a 150 nanosecond part. So the part is guaranteed to work at 5 volts and have stable data on the output after all of the pins have become, whatever state they're going to be in. The rows latched in, the columns latched in, the RASCAS stuff that goes on here. The part's enabled and you're waiting for the data out to become stable. 150 guaranteed to be stable at 150 nanoseconds. So let's put the 64K part back in. And we are set at 150 nanoseconds. Let's test. And we can see that it looks happy with that. And let's go to the lower voltage here, the 4.5 volts. And let's go to the 5.5 volts. And I'd be happy calling that a DRAM that matches the marking. So it's a 150 nanosecond part. We're at -15 here. And we've done what I call a VCC margin sweep, what's called in the industry. And that is lowering the VCC power and raising it will affect the part. And it'll typically slow it down. Although it might speed it up a bit. It's like overclocking a modern CPU where you change the voltages to get clean overclocking. This VCC margins is a test that the part is, working as expected. And if you've ever serviced an older machine and you get in there and look at the 5 volt rail, it might be 4.9, it might be 5.05, it might be 5.1. Typically, VCC is spec'd to be within, 5% or 10% or some value in the machine. And you see machines with VCC of 5.2 or 5.25 or 4.7 or 4.8 volts. And they seem to run fine. But what that offset, when it's not on 5 volts, it can affect the operation of the parts. So let's see how fast this part really is. Let's go to, actually that's 0. Let's go to 140 nanoseconds and see if it still passes, and it seems to. Let's go to 130 and see if it still passes, and it seems to. Let's go to 120, and it still seems to. 110. It seems to. 90. At 90 seconds, or 90 nanoseconds, it started to finally fail at 5 volts. So if it's marked 150, why did I have to go all the way down to 90 before it failed? So there's also what's called guard banding. And guard banding in the industry means even though I'm selling you a 150 nanosecond part, I'm actually faster than that. The part is actually faster than that, and that helps guarantee that in your application the part will work at 150. If I've tested these at 130, say, and I've guard banded by 20 nanoseconds, the odds are really good it's going to work in your application, expecting 150 nanoseconds. Guard banding also is true around the power rails about, I will operate higher than 5 volts, I'll operate lower, and guard banding is about giving enough space around those values or below an access time that the part will work in most or all applications. This guy came all the way down to 90 nanoseconds and failed, so let's take him back up to 100, and he seems to work. And let's go to 4.5 volts and see what happens. And at 4.5 volts, the part fails. So it's just what I was saying before. VCC matters. Let's come up to 5.5. And it's passing at 5.5. Let's go back to 4.5. So the part doesn't operate at 100 nanoseconds at 4.5 volts. Let's go up to 110 and test. And it works. So at the nominal 5 volts, what did we get to? I think we got to 90 nanoseconds before it failed. So we were at 100 when it worked. When I went to 4.5 volts, we had to go to 110 before it worked. So there's, that demonstrates that VCC makes a difference, that access time is important. And like I said, as the vintage machines you look at that use these kind of RAMs, become faster and faster. As the CPU is clocked faster and faster, these things matter. And like I said, my Commodore 64 has a bad DRAM, and I remove it, and I put a socket in, and I drop a new one, just a random one. Here's talking about random parts. Here is a bunch of 256K and 64K DRAMs, and there's some other stuff mixed in here as well. There's some Micron parts that are 200 nanosecond. There are -20s. There's some NEC parts that are 150. There's a 256K over here that is an 80 nanosecond part. There's some Oki data parts. We've got one of these we've been playing with at 150. I don't think those are DRAMs. These are 1 megabyte by 4s, I believe. We can't test them in here. But there's this mix, and everybody that's been doing this for a while has a few, at least, DRAMs set aside. I'll say it for the upteenth time here. As the machine speed clocks faster, it matters. And it matters more and more that you have a part that is fast enough for the application. So let's come back to 5 volts nominal. I think I spotted some -80s here someplace. Maybe. And maybe not. Those are 200s. Well, let's drop in one of the Microns. The Micron DRAMs have a really bad name. They're known to be flaky. They're known to fail even when they're not in operation. And there seems to be pretty good evidence that's all very true. So let's drop this one in. It's a -20. It's going to be 200 nanoseconds. I would expect it to fail here at 110. We take it up to the full 150. So it does seem to operate at 150. So there would be some guard banding on this. It'll be faster than it's labeled. Let's look at it at 4.5 volts. It fails at 4.5. At 5.5, it seems to be okay. So, would I use this part in an application that needed a 150 nanosecond part? No, I really wouldn't. Because if the VCC rail is low, someplace under 5 volts, there is a point the part will fail. You see it demonstrated here with the E. So, I see a lot of, it's a Micron part, it's bad, let's just replace it. I dropped it into my test device, like my retro chip tester, and look, it seems to be good. I'm confused. How could it be bad and be good? Well, this explains part of it. The retro chip tester is not testing at full speed like this does. It is doing a gross functional test. It's not testing at 200 nanoseconds or 100 or whatever. I believe it's testing slower than that. I haven't measured it, but I would be very confident that it's testing slower than even 200 nanoseconds. Potentially, Stefan would need to talk to that, or Steven, however you pronounce his name, would need to talk to that. And so while the retro chip tester is a really awesome device, and I use it a lot for a lot of parts, it's not guaranteeing access time. It's not guaranteeing VCC margin. So as you saw here with the voltage lower, this part failed at 150, but at 5 volts it worked at 150. It's quite possible with these Micron DRAMs or any kind of memory device that over time the part is degrading. It hasn't failed, but it's degrading, and it's getting slower. Or it's been ran for a long time at greater than 5 volts, and it's damaged the part where it's making it run slower, but still functionally, if you look at it slow enough, it works fine. So I hope that makes some sense and might explain some of the weird things you occasionally see in videos where somebody's just basically like, wait a minute, why did this part be bad in the system and come out and be good? So here's an 80 nanosecond part. It's I believe that's a Mitsushimi, I can't even say it, Mitsumi symbol. It's an MN41256A-08. The -08 to me reads as 80 nanoseconds. And that would be a normal marking in the industry at the time. So I would expect this to pass at 150, just no problems. 256K, it seems all hunky-dory. I would expect at 4.5 volts it to be nice and solid. I would expect at 5.5 volts it to be nice and solid. We are so guard banded here. We are testing 70 nanoseconds slower than the part the markings indicate. So let's get down to 100 nanoseconds. 5 volts, I would expect it to be nice and solid and just work well. So we saw a different pattern show up there. If I don't know if you noticed it, where the bottom segments became an upside down U, and I don't know what it means when it does that. I really don't. I know that when you get the high segment lit, it thinks it's testing a 256K. When you get the low segment, it thinks it's a 64K. There's that U again. And I don't know what it means. I'd sure love to find a manual for this. If you know where I can get manuals for these, I'd love to have them. I've been to the Innoventions website. The website is still there. Apparently, the guy who designed all this has passed. And due to COVID, they've just let the business close, but the website is still there, and they're still supporting that latest generation memory test device. I think Adrian's Digital Basement demoed one of their last generation devices, but there was no historical manuals. There was nothing for this stuff. So, no, but 4.5 volts. That part is pretty unhappy. And at 5.5, it seems to work. Now, 4.5 to me is pretty low. So I'm not surprised we saw a failure. Well, this time around it seems to be working. So it's marginal at 4.5. Let's get down to the rated speed, 80 nanoseconds, 5 volts. Let's make sure we're doing a clean test. And I would expect it to work here. I mean, this is what this is where it's guaranteed to work. 5 volts, 80 nanoseconds. Let's see if we can get it down to where we get a failure and see how slow or how fast it really is. That's a 60 nanosecond test at 5 volts. I'm really thinking that upside down U just means and at 40 nanoseconds it failed. You see the E there. So again, it's guard banded, and in the Japanese stuff I'm testing here, the guard banding looks to be nearly 50%. So, you know, the part's 50% faster than the marking, and that might make perfect sense. You know, from their data sheet and their thinking behind the scenes. Partly because if we come up now to 50 nanoseconds and we go to 4.5 volts, I suspect it'll fail, and it did. So again, they have to guard band against both expected access time and the power rail. You know, like I said earlier, the power rail, the voltage can matter, and the further it is off the 5 volt or the 3.3 or whatever the part's spec'd for, the further it is off of there, the higher the odds the part's going to fail. So at 50 nanoseconds, 5 volts, it worked. I think at 4.5 it failed before. Yeah, it failed. Let's take it up to 60 or 60 nanoseconds, and maybe it'll pass here now. So I hope this starts to make some sense about the power affects access time. You know, the voltage affects access time. It just does. And then there's an expectation of how fast the part is. So we've kind of demonstrated it here. You can go in and vary voltages and look at access times and things and create what's called a shmoo plot. A shmoo plot is basically voltage versus access time and where the part operates. And you get this kind of space that'll have a shape to it that looks a little bit like a shmoo from an old comic strip from like the 40s, I think. It was some kind of weird animal. But anyhow, it's got this particular shape. It's called a shmoo plot, where it would give you an idea of the range of voltages and how they affect access time. When I worked on EPROMs as a test engineer, I generated loads and loads of shmoo plots, programmed the equipment to vary the power voltage and measure the access time of the part. To create those, to give us an idea of, you know, is the part well centered around 5 volts, etc. The other thing just to mention here is back in the days of 5 volt, parts were much more tolerant to movement above and below 5 volts. You get to the world of 3.3 volts and parts are less tolerant. They want a more 3.3 volt power supply. And when you get down to 1.8 volt logic, they really want 1.8 volts. And you know, when you've only got 1.8 volts potential, it's hard to have a half volt, margin to either side. It isn't going to work. So, and that gets into why in modern machines those voltages really matter more than I'm in a Commodore 64 and look, it's at 5.15 volts. It's close enough. It's within spec. It'll work. And you would never on a 1.8 volt machine say, look, it's 1.1 volts. It's only off by 0.7. It's good enough. It'll work. The world just doesn't work that way. So we'll take you back up to 80. We'll test here at 4.5 volts. It's happy. At 5.5 volts, it'll be happy, I believe. And of course, at the nominal 5 volts, it's happy. So hopefully there's a couple takeaways from this video. If you ever come across a set of these and decide to buy them, or any of the add-on modules, like the 1 megabit module, and you wonder what this ribbon cable's for, like I did when I first got these, well, there it is. There's the core system to check, and then there's add-on modules that used a ribbon cable. So that's kind of cool. This, like I said, the only reason this really caught my attention and I spent the money was being able to actually vary access time. It's kind of a cool thing. And of course, be able to access voltage. It's kind of a cool thing. So, is there anything else to be said here? For a gross test, I said it several times, the retro chip tester works really well. I'm very pleased with how it works. I'm very pleased with the support there's been on it. I've worked with, I believe it's Steven or Stefan, I don't know. I've worked with him on several device definitions where they needed to be tweaked. He's really good to work with. He supports the product. It's, by the time you bought all the parts and stuff, that it's spendy, but it's a nice tool. It just covers such a wide range of parts. And, it's getting smarter and smarter all the time. Great device, but testing to speed in VCC margins accurately is much more complex. And it requires more specialized hardware. And this just gives me another piece in my little arsenal to be able to test. And like I say, in this case, it's 64K, 256K DRAMs is it. But, it's a nice capability to have. It'll get added to my collection of test gear. Probably never used beyond this demo, honestly, but it may be. Who knows? Anyhow, anything else to say here? If you got this far into the video, I certainly appreciate it. Likes help. Comments are good. Negative or positive. What did you like? What didn't you like? I read them all. I reply to a fair number of them. Don't always reply. It's just reality and time. But, I'm happy to share this kind of stuff with you. It's kind of a neat capability. I'm happy to have discovered in an eBay listing how this cable works, because I really saw this as an independent device. It just confused me about why that ribbon cable was hanging out. And it confused me about, well, it's only got a red LED. How does it tell me good or bad? It never made any sense until this connection between them. So I guess I'll wrap this one up here. As always, I can ramble on forever. I don't want to do that. I guess we'll talk soon.